In this video, I'm going to be going over how to calculate the pH of a buffer solution throughout a titration using a titration curve. So if we were to start with a beaker of water, and in that beaker, we're going to see HA, which we can call a weak acid, we know that when we go to run this titration, we are going to add a strong base to this solution so we can remove some of this hydrogen and we can start to form some conjugate base. So we know that is the titration that is going to be run. So we can assume we're going to add strong base. Let's pick OH minus hydroxide to add in. So what we can do is we can track the pH of this buffer solution over time using a titration curve. So the units on this titration curve are going to be pH. And in this case, we're adding a strong base. So you will see in a titration curve, the milliliters of whatever you're going to add. So the milliliters of OH minus added. So we can pick 0, 7, 14 for the pH. Let's call this at 25 degrees Celsius. So the milliliters of OH minus added is going to determine how much base we have put into this beaker and how much conjugate base of HA we are going to create. So let's track this beaker as we add some base to the solution. So let's calculate the pH before we have added any base. So when we are at 0 milliliters of OH minus added. So we have HA and H2O. So we know the reaction that is going to be run is HA aqueous plus H2O liquid goes to H3O plus aqueous plus A minus aqueous. Now, in order to calculate the pH, I'm going to do this without numbers or values. I think it's more important to get the concept down. This will be the same for any titration curve before we have started the titration. All we would need to do is know the initial concentration of HA. Well, let's at least just plug in 1 molar of that. But let's leave our Ka unknown. So we know we have 0 of this, 0 of this. Now remember, we are working with a weak acid and water is our weak base. So we know we cannot call this a 100% yield reaction like we can when we start the titration with a strong base. We are still working with a weak acid and a weak base. Now remember, a weak acid when reacting with a weak base will react only slightly in the solution. So what we have to say is that this is going to simply react minus X. We don't really know. Weak acids are going to react based on their Ka value. So this is going to be 0 initially and 0 initially. Now remember, when we are working with a weak acid, we approximate that because this is a weak acid and it barely wants to give away its hydrogen, 1 molar minus whatever is going to react is going to be very, very small. So 1 molar minus that with significant figures will stay about 1 molar. So we're going to add in plus X and plus X. This is going to be X and X. So how can we solve for the pH at this moment in time? So we know pH is the negative log of our H3O plus concentration. So how do we solve for H3O? Well, we know the Ka is equal to products over reactants, which is H3O times A minus over HA. So if we know Ka and we substitute in X, and 1 molar into this expression, we can see that we're going to be left with Ka equals X times X over 1 molar. So all we would need to do is Ka, and we could solve for X and take the negative log of that, and we would have our pH. So this is the start of a titration. So we have not added any OH minus yet. So the titration has yet to begin. So what happens when we start adding OH minus? So what we can see is that we're going to start forming some conjugate base. So let's continue our discussion. So now we have HA. We're going to add OH minus, which is a strong base. So one thing that we definitely need to get comfortable with when we are working with titration types reactions is working with moles. So when can we work with moles and when can we not work with moles? So you can work with moles when you are dealing with a reaction where something strong is involved. So because we are adding OH minus in, you will often see in titration type questions, moles be the unit used to work with your calculations. However, if we are working with a problem like this at the start of a titration before anything strong has been added, we cannot use moles. So we cannot use moles. We have to use concentration. And just to repeat that, you cannot use moles when you are reacting a weak acid or a weak base with water, which is also weak, because nothing is strong. We do not know how much of that acid or base is going to react. We need to set it equal to its Ka to solve for how much is going to be left over and how much H3O plus we're going to form. So we cannot use moles for a weak acid or weak base reacting with water situation. However, when you are reacting something with a strong acid or base, you can use moles because we know from our calculations prior that it is a 100% yield reaction. So if you were to start with 1 mole of a acid and you react a certain amount of moles of base, you can simply set up your ice table. So it is a subtraction or a limiting reagent type problem. And the moles you can simply subtract to get your answer. So again, you can only use moles when you're reacting something strong. So let's see how this plays out. So let's say that we start with 1 mole of our weak acid. So let's say with our titration curve, keeping track, that we want to add 500 milliliters of our base. So if we add 500 milliliters of our base to, let's say, 1 liter of H2O, we need to know one more piece of information. We need to know the concentration of that OH minus solution that we are adding to our beaker. So when you run a titration, you have your original beaker with whatever you're starting with, and you are adding a solution of OH minus to that beaker. Now, in order to calculate how many moles of OH minus you need to add, remember, molarity is equal to moles over liters. So we need to know how much of that OH minus we are adding in terms of its milliliter value and the concentration of the solution that we are pouring in. So we know that it is a 500 milliliter value that we are adding, which is 0.5 liters. And let's say we're working with a 1 molar solution. So the OH minus solution that we are adding is always going to be 1 molarity. The only thing we are changing on this x-axis is how many milliliters of that 1 molar solution that we are adding in. So let's see how many moles of OH minus this is going to give us. So 0.5 times 1. So we're going to add 0.5 moles of OH minus. So we add 0.5 moles OH minus. Now let's see what's in our new beaker. So now we added 500 milliliters of another solution in, and we started with 1 liter of water. So now we know we have 1,500 milliliters, or 1.5 liters. So we have 1.5 liters of H2O, and we know we have 1 mole of HA, and we said that we added 0.5 moles of OH minus. So, like we have seen in previous videos, we need to draw an ice table for this beaker. So we'll move this. So let's draw an ice table. So now HA is not going to react with water, it is going to react with OH minus. It is a strong base. It wants to react with that strong base more than water, which is a weak base. So we have HA, aqueous, plus OH minus, aqueous, goes to H2O, liquid, plus A minus aqueous, and this is great that we have now formed some conjugate base in this reaction, which can help us create a buffer. So an ice table. Now remember, because this is a reaction, we're reacting with something strong, we can use moles. And I'm using moles because often titration problems use moles. They will give you a milliliter value and a concentration, and you have to get moles to work with that concentration in that ice table. So remember, we can use moles because we are reacting something strong, but if it is not strong, you have to use concentration, like I did in this part of the problem where the titration, I should say, has not started yet. So let's fill in our ice table. We have 1 mole and 0 moles. So very similar to how we did this ice table in previous videos, we can simply use a limiting reagent type method to solve this ice table. So we have 0.5 moles of base and 1 mole of acid. So our base is going to run out first. So we know 0.5 moles is going to react, and we'll be left with 0 moles. Now, the acid, HA, wants to give as much hydrogen as it can to the base because it's strong, but there's only 0.5 moles of base to accept its hydrogen. So we could only react 0.5 moles. When we left with 0.5 moles, we're going to make 0.5 moles of the conjugate base in the meantime. Which we can now see will give us a leftover beaker with 0.5 moles of HA and 0.5 moles of A minus. And it is good because if we want to create a buffer, it is good that we used up all of our strong species. So let's see how we can calculate the pH after we have now run this titration with a certain amount of strong base. So I'm going to draw a beaker using what we have left over on the next page. So we have H2O in our beaker. We have 0.5 moles of HA and 0.5 moles of A minus. 0.5 moles of HA and 0.5 moles of A minus, and we have 1.5 liters of H2O. That's because we started with 1 liter of H2O and we added 500 milliliters or 0.5 liters of that 1 molarity solution of OH minus. So we have a total of 1.5 liters. So how could we calculate the pH of this beaker after this point in the titration has been completed? So we are not done yet. We need to calculate this last step in order to get our pH, because so far in this problem, we have not seen any hydronium yet. So you can only calculate pH once you have a concentration of hydronium, which is H3O plus. So let's continue to see if we can make an ice table where hydronium will form. So in this case, I'm going to pick HA as our acid. Now there is no OH minus left to react with HA. So what base will HA react with? Well, one thing to note, you will never react an acid with its own conjugate base. That will never happen. So HA will react with the best base available, which is water. And this will create H3O plus when this hydrogen is given to water plus A minus. Now ice table. So what we need to remember here, there is nothing strong in this ice table. HA is still a weak acid, and we have nothing left of our strong base in the beaker to react with it. So we need to remember that we cannot use moles anymore. So we have to convert these mole values back to concentration if we are going to fill in this ice table. So 0.5 moles divided by 1.5 liters is going to give us that concentration. So 0.5 divided by 1.5 is going to be about 0.333 molar of HA. And remember, we cannot keep it in moles because now there is not a strong reaction going on. There's a weak acid with a weak base. We never keep track of water. H3O plus, we don't know. There's nothing in there so far. A minus, we do have a concentration of A minus when we start this reaction. It is 0.5, also divided by 1.5 liters, which is 0.333 molar. So what is going to happen? Well, there is no hydronium to start this reaction. So we want to run this reaction to the right to produce some hydronium, right? So this is going to start to give away some of its hydrogen to water minus X, because we do not know how much is going to react. It is a weak acid, but because it is weak, we can say that because we can use an approximation that it is weak, this will stay 0.33 molar. Now, hydronium will be plus X. This will be X. Now, this will be plus X. But for the same reason that we can approximate this as minus X, in a little bit of that hydrogen, I should say, will be donated. We can say that 0.333 plus a very small amount will still be 0.333. So it works in both ways. So how can we calculate the pH using this ice table? Well, we need the Ka, A minus times H3O over HA, and we can fill in. We don't know H3O, we can call it X, and this is going to be over 0.333. Now, if we had the Ka value, we could simply just cancel out this 0.333 on the numerator and denominator. It's not always going to work out like that, but it did this time. So if we had the Ka, we could solve for X and simply take the negative log of that, and that would be our H3O, and that would give us our pH. So we can see, using a titration curve, we can see as we add strong base to our weak acid, we can calculate how many moles of OH minus we're going to add and solve with two separate ice tables. One, which is the strong reaction of HA and OH minus. We can simply use moles to calculate. Then with our leftover beaker from that reaction, we can then use another ice table that we remember we can only use molarity in this ice table because it is not a strong reaction, and calculate the pH from there.